Hello YouTube. Today I will be discussing my all-time favorite theorem, the General Stokes theorem. And you'll soon learn why I love it so much, and I hope you'll come to appreciate it as well. So to begin, I will assume you have a somewhat basic understanding, or at least a somewhat basic understanding of calculus, in terms of what an integral is, what a derivative is, because it will come in handy. But I will pretty much explain the rest, so don't worry if you haven't taken multivariable calculus, you have no idea what that is. That's what I'm here today for, right? So to begin, I want to talk about a couple of things. The first thing are differential forms and this thing. So now if you've taken pre-calculus or integrated mathematics 3, you will remember this guy as this sort of R with two lines as all standing for all real numbers, right? In terms of you writing your domain and your range, right? Well, what we can do is we can add a superscript to this guy, typically for when n is greater than or equal to 1. And we can essentially say, this is how many, you can think about it in what the number n represents as the number of dimensions we're going to be considering. And that's really key to multivariable calculus, is how many dimensions you are considering. And the most common, and probably the one we're most familiar with, is R3. You should call it R3. And that's our 3D space. We have our x, our y, and our z. That's kind of the typical standard number of dimensions. That's what we are most capable of thinking about. Up, down, right, side to side, and then forward, back, right. Okay, so we'll be talking about R3, but just be aware, everything I'm talking about today, you can generalize it. And that's the beauty of the General Stokes theorem, it's its generalizability. Okay, so let's get back to differential forms. You'll hear this, I'll talk about this thing called a k-form. And a k-form, all that is, well, all k is a variable. It's a number. And k goes up to n, what our n is. And in this case, we've said n is 3. We are doing 3 dimensions. So, okay, well, we can have 0, 1, 2, or 3 k-form. Well, what is the k-form differential? How does it look like? Well, if we have 0, that means it's simply this function f of x, y, z. That's it. We have no differentials. It's not even really a differential in the sense what you might think it is. There's no differential attached because it's a 0, right? Makes sense. Okay, well, if we have a 1 form, we would say, okay, we're going to break our function into component functions, and it's going to look like this. So all it is we have some function times dx, some function times dy, some function times dz. And of course, this is because we're going to n equals 3 for our number of dimensions. And of course, you could keep going. But for the sake of our sanity, I'll just do 3. So, but it's only, so one form, so this k corresponds to the number of differentials. In this case, 0 had nothing here, right? 1, we have a dx, a dy, a dz. Okay, what about a 2 form? Well, again, we have our function f, or p of x, y, z. But instead of times dx, we are now going to be multiplying by dy, dz. And then for q, we're going to be multiplying by dx, dz. And then finally for our r, and then we're going to be multiplying by dx, dy. Okay, and then again, 2, because 2 differentials attached to each function. Then finally, for our 3 form, it's just going to be a function, some function, right? We can call it f, times dx, times dy, times dz. So that's all. So k-form is simply referring to the number of differentials we have in any given, attached to any given function. So, not too bad, but just something to keep in mind. Okay, and so the next thing I'd like to talk about, another thing you'll see pop up, is this thing. No, it's not a caret, it's a wedge. So we talk about differential forms. So if I have a k form omega and an L form eta, such that their sum, the k plus L, must not exceed the number of dimensions we have, in this case 3, you can express the multiplication of two differential forms using a wedge. So there are a couple important properties. I won't go over all of them, but there are a couple. The first one being, so if I were to say dx times dy, that's one differential times another, I can say that this would become dx hat, or wedge dy, right? I can just write this, this is really, like omega times eta, I'm writing in terms of wedge product. Okay, so now another important property is anti-commutativity. You can't, dx times dy is not dy times dx. Kind of like the cross product, what you can say is this is going to be -1 times dy wedge dx. So that's an important thing. Now, I think the most important property is if I were to write dx times dx, I could expand that as dx, wedge dx, I end up with 0. If I have one differential form times itself, I get 0. Now that is really interesting and will be incredibly helpful for some later proofs. So just keep this in mind. And then of course, in terms of addition and subtraction, you can add two k forms by simply combining like terms. Nothing too tricky there. But the multiplication is what's going to be really important. The other thing is you can distribute your multiplication normally. So if I had, like omega times, dx plus dy or whatever, I could just distribute that and then use the wedge product to represent those products. So that's the wedge product. And then another thing I'd like to talk about, are vectors. Just because you may not have had vectors and I may be losing you. So hopefully I don't lose you. Let's say we have a vector f, right? Because we're R3, I can say that could be a function, so it's a vector function containing scalar functions that could be defined like this. And if you notice from when I was talking about differentials, the common nomenclature is using p for your I, if you're used to unit vector, your q for your j, and r for your k, in terms of x, y, z for vectors. So just pretty basic. Another thing, I will be using these bracket-looking things. They're called chevrons. I will be using them as opposed to unit vector notation, because unit vector notation sucks and is terrible. And chevrons are so much sleeker and a lot easier to write. So we'll just be using that. So just for your edification. Okay. Another thing, and I know it's a lot, just bear with me, it's going to make what I say later a lot easier to digest. Another important thing is this. It's the Greek letter delta. But we can think about it in terms of a derivative. This is a partial derivative. And I know hopefully you've seen this before. It's analogous. This is d, but this is delta, Greek letter delta, which we would just, I will call it del. It's easier to say. So hopefully you're familiar with this, right? If I'm taking the derivative with respect to x of 5x, well, I just get 5. But now in multivariable calculus, I've already said we're dealing with many variables. So if I have a function that I want to take the derivative of, say 5xy, well, I can't, this is not valid for this, because I can take the derivative with respect to x and with respect to y. So in this case, I'm saying I want to take the derivative, the partial derivative, because there's more than one variable. I'm going to take the partial derivative with respect to x, meaning x is my variable I'm differentiating, right, with respect to. So that means all other variables, I could have z's and w's and o's and p's, whatever. They are treated like constants. So this becomes simply 5y. So just kind of interesting, basic partial differentiation. I mean, this is basically covering a lot of multivariable calculus in like 10 minutes. So if you're sticking with me, great job. Okay, so the last thing, well, second to last thing, before I can finally give you the general Stokes theorem, is I want to talk about a k-manifold. Hopefully you remember k from my discussion of differential forms earlier. So you might be saying, what's a manifold? Well, a manifold is simply a set of points. It could be a line, a surface, a solid, anything upon which a function is defined, right? It's simply, so a manifold is just, it's something on which a function is defined. It's you could think of it like a region, right? A region is probably a good way to describe it. It's an area on which, and it could be points, it could be some kind of a curve, it could be some kind of a surface, some kind of a solid, upon which I have a function that is defined there. I'm integrating over that, and that's going to come important. That's going to come in handy. Will be important. And well, I'll use the letter M for manifold. I think it technically it's uppercase omega, but M is easier to draw, and it's also a little bit more straightforward because M for manifold, right? The one-time nomenclature in math kind of makes sense. So M, right? And so K, think about this in terms of the number of dimensions. So again, we're sticking R3, so the biggest K could be is 3. So I could have a 1 form, a 2 form, a 3 form, right? That's the number of dimensions. So whether I'm talking about, this is like a 0 form, like I'm talking about points, right? Like a set of endpoints, or if I'm talking about 3, then that's kind of, it's a 3D shape. So that's all this is. Now the other important thing is I will use this. Remember our del operator, or our del symbol rather, del M from partial differentiation. This is the boundary. This is the boundary. The boundary of the manifold. So it's just what's on the outside. And I'll go way more into this, but that's what this is the boundary of the manifold. This is the manifold itself. Okay. And as one last thing, we're almost there. One last thing, omega. This is the Greek letter omega. If we said our manifold was a K form, then this is a K-1 form. For it's a K-1 differential form. And if you think about it, it kind of makes sense. Our boundary of our function is going to be of a higher dimension than our function itself, because it just mathematically it makes sense that way. So omega is our differential form, K-1, and our manifold is going to be a K form. All right, we have finally made it to the general Stokes theorem. Oh boy, this is exciting. This is exciting. Okay, are you ready? All right, I think you are. So, the integral of the boundary of the manifold of our differential form omega. This is equal to the integral over our manifold of d omega. This is the general Stokes theorem, and this is what is so cool about it. Because this is the very epitome of mathematical beauty, elegance, and utility. Just the raw power expressed in this theorem is just, it's just crazy, because This is the very essence of calculus because it explains the fundamental theorem of calculus. And the fundamental theorem of calculus is higher dimensional extensions. This explains calculus in a nutshell. It's a very key concept. And understanding and mastering this, it is going to allow you to access all of that power. Not only to mention, it is a very useful tool for remembering all the different equations that I will be going over momentarily. So it is just absolutely elegant, beautiful, amazing. I would have to say just, maybe just a little bit better in my mind than Euler's identity, which was my last video, which is incredible in terms of its beauty. So I definitely recommend you watch that if you have not. The General-Stokes theorem is just absolutely fantastic. But I could wax poetic about the poetic beauty of the General-Stokes theorem for hours. But I won't do that. I will get you the information you need. So, okay. Well, let's just kind of talk about this, and then I'll break it down. So, okay, so we're saying on the right side here, the integral over the manifold, over whatever region we're defined. So the integral over the region we're defined of the derivative of a function is going to be equal to the integral over the boundary of that region, but of the original function. What? Okay, I'm going to erase this and we'll take a closer look. So, okay, so on the left, I'll write what I had on the left before, which is the integral over the boundary of our manifold, but of the function omega. On the right, that is going to be the same, that's going to be equal to the integral over that entire manifold, but of the derivative of that function. Okay. So, let's start applying this to some of our formulas, shall we? Okay, well, for the fundamental theorem of calculus, if we are integrating from a to b of a function f prime of x dx, that is going to give us f of b minus f of a. And you can think about this, that if we have some some region, this is our entire region, this line right here, this function, going from a to b. The integral of the derivative over this entire region is nothing less than this value minus this value. So this, you can kind of think of this f of the b minus a, that's the endpoints. That's the boundary of a because a line, this is a one form, so you can think of the boundary then of a zero form. Well, it's just points. It's the end point and beginning point. So our endpoints really are our boundary, and our entire line, our entire function then is just our region. So okay, so now we kind of have a way of understanding and explaining why the fundamental theorem of calculus works using the language of the General-Stokes theorem. But the whole point of the whole beauty of the General-Stokes theorem is the generalizability of it, that we can extend it to an infinite number of dimensions. So let's keep going. Okay, so let's talk about the fundamental theorem of line integrals. And now a line integral you may not have heard of, but what that is, fundamental theorem of line integrals says that if we have a vector function f, a vector field rather, f, if it's conservative, in other words, as you travel along some curve, right? Traveling along, or a line, if I'm a line integral, right? You're traveling along some path. It doesn't matter which way you travel, whether you're going forward or back, you're going to end up with a net flux of 0. And your energy is going to stay the same. So it's a conservative field. It doesn't matter how we travel. It only matters where we start and where we end. And that is important. And gravity is a great example of a conservative force field. Like if I'm here, I have some chalk here. I move it up here. In terms of work done by gravity, I only care about my position where I ended and my position where I started. I could have gone, and then end up here. Doesn't matter. Only the difference in the height. Only where I started, where I end. That's what's important. And this is saying, the integral over the line integral, like curve over the curve C of grad f dot dr, if r is our parameterization, that's going to be nothing less than f of r of b minus f of r of a. And you can think of this as if I have some curve, right? Say this is r of b, this is my ending point, and this is my r of a, my beginning point. I don't care about this path. I only care about where I started and where I ended. Again, because this is the entire region, right? It's my line integral. And this is just the endpoints. Again, that's the boundary. The endpoints are the boundary in this case. So quite interesting. And this is a quite interesting technique for solving line integrals when you know that f is conservative. And if you're interested, you can show that f is conservative if there's a function f, or if you have a vector field f such that the gradient of f is equal to f, big F. In other words, or the curl of this is 0, meaning as you go around, it doesn't matter which path. It only matters where you start and where you end. And of course, if you go around a complete circle, if I were to bring this right back, then my answer would be 0 because I started where I ended. Therefore, there's no change. So kind of interesting. All right. Well, let's keep going, right? So now let's talk about the generalized Stokes theorem, which says that the surface integral, right, of S, over S, our surface, of the curl of f dot ds, that is nothing less than the line integral over C of f dot dr. And a way of visualizing this guy is if we have some kind of curve C, and then we have some kind of surface kind of rising. You can almost do this like the C is kind of like our pancake, and the surface is kind of rising out of that. So it's actually like, imagine if you have a pancake and you're kind of, it's basically a pancake. The line integral is what's running around it. It's around the edge. The surface is what's on the top or the bottom, right? So then this surface is S. And the curl of F is nothing less, than the gradient vector cross F. And I'll get into more why this is important. And the final theorem, or rather formula we'll look at, is the divergence theorem. And this one says that the triple integral over a solid E of the divergence of f dv, we're saying that is the same as the surface integral of f dot ds. And a way, move that eraser out of the way, and a way of visualizing this guy is if, imagine there's a sphere, right? I mean, you know what a sphere looks like. I don't have one with me, but if you have a sphere, right, like a basketball, let's say that basketball is a unit sphere. Let's say we slice it in half. So we kind of have, you know, this circle, right? And then we have kind of this spherical half still coming out of it. Well, that unit circle on the bottom is a surface. So is this thing around the edge. It's a surface. It's like if you were to peel off the leather on the basketball, if you're to take that out, you kind of have this this surface area, right? Well, that's what the surface is. It's like the eggshell or the covering, kind of, right? And then, okay, well, the entire region is then E. That's our solid, right? Okay. Well, let's look at these and just see how they relate to the general Stokes theorem. So we kind of talked about this and this. So the curl of f, as I said, is merely a derivative. It's a form of a derivative. That's kind of what the gradient pseudo-vector is, and I won't go into that. But it's a form of a derivative. And so we're saying that the integral over the entire region, this is the surface, like our pancake top, that entire thing. The integral over that of a derivative, right, of a derivative, is just the same as the integral over the boundary, right, as we go along this curve, kind of that edge around the pancake, of the function of f, of our vector field f. We're saying those are equivalent. And so that fits general Stokes theorem. And if we look at the divergence theorem, we're saying the triple integral over E, over our entire manifold, our entire spherical region in this case. Over that, of the derivative, the divergence is nothing less than the gradient dot, or the grad dot f. Another form of a derivative, different, but the same idea, the derivative. And over here, we're just taking the integral over the surface, right? Over our surface, over the boundary, like the outside of that half-unit sphere. And we're taking that, we're over that region, just of the function. So these are the major fundamental theorems that you need in multivariable calculus. But you can see they are all the same, they're all varied expressions of the same idea, which is beautifully encapsulated by the general Stokes theorem. But this has all been a little conceptual, so for those hardcore math students, I think you want to see a real proof of this. And now proving the general Stokes theorem, that is something that I have yet to do, and that goes way beyond multivariable calculus. But I can prove for you the divergence theorem, that the divergence theorem is equal to the flux. The divergence is equal to the flux by using the general Stokes theorem. So why don't we do that as a nice way to close? Kind of solidify the conceptual understanding, hopefully, that this helped establish. Dirty blackboard. Okay. Well, the first step in this proof is going to be writing an applied definition of the general Stokes theorem. So, because we know we are going to be dealing with a two-form manifold, right? It's a surface. We know we're going to need two integrals of omega, right? So the boundary. Okay, and then we know we're going to be wanting to make this to a one more k, so this is going to be a 3. 3 form over E of the divergence. Oh, shoot, no. We don't know that yet. Just d omega. Okay, so this is our applied definition of the general Stokes theorem. So let us continue. Let us say omega is equal to p of x, y, z times dy dz, remember, because it's a 2 form in this case, plus q of x, y, z dx dz plus r x, y, z dx dy. Kind of running out of room. Running out of room there. Then let's say we have a vector field f, and this is going to be nothing less than p of x, y, z, q of x, y, z, and then finally r of x, y, z. Okay, well, let's deal with this left-hand side first. We're saying the double integral over our 2 k form manifold, right, or surface of omega. Well, what is this? So we have P, Q, and R, right? P, Q, R. That's P, Q, R. We can define, that's defined as F. We're multiplying by dy dz, dx dz, dy dx dy. This we can say then is nothing more than the double integral over s of f dot ds. ds is going to give us our dx dy, comma, dx dz, comma, dx dy. That's what ds is. And f, we've already said, is going to give us our p, q, and r. So we've already established that the left-hand side is equal to the flux of f, right? This is flux. Okay, so we're halfway done, right? Okay, yay. Well, we need an expression for dw. We need an expression for dw. Or g omega. Not w, it's omega. Okay. Well, let's just take the derivative of omega. And for space's sake, I won't rewrite this whole thing. But if we just take all of this, we take the derivative. Remember what I said earlier about differential forms? How you can distribute them? We can distribute this derivative to here, here, and here. So we can say we're going to have the derivative of p times dy dx plus the derivative of q times dx dz plus the derivative of r times dx dy. So what we can do is we can say, okay, well, that's going to be derivative of p times dy dx, or dy dz rather, the derivative of q dx dz, the derivative of r times dx dy. Okay, we've just simplified this, we just got this expression for the derivative of omega. Well, remember how I also said when you're multiplying a differential form, you can just, instead of writing them like this, you can just write in a wedge using wedge products, right, from differential geometry. Let's do that. Okay. So we've got that now. But now we need to expand the derivative of p, derivative of q, derivative of r. And this, remember how I was talking about the delta in terms of partial differentiation? That's going to come very in handy now. Because we saw earlier, our function p right? That's a function of x, y, and z. Q is a function of x, y, and z, and so is r. So you can't just say the derivative of p is blah. Let's talk partial derivatives. So we can say, I'm going to go over here for space's sake. Del p del x dx plus del p del y dy plus del p del z dz. But we've just expanded the derivative of p, wedge dy, wedge dz. We're going to do the same thing for q and r. Do that kind of quickly. Same idea. Del q del x dx plus del q del y dy plus del q del z dz. And we're going to wedge dx and we're going to wedge dz. And then bringing this guy up here for sake of space, we're going to say this is going to be del r del x dx plus del r del y dy plus del r del z dz. And we're going to wedge dx, wedge dy. Now remember when I was talking about the properties of the wedge product? That's where this will start to come very in handy. So, remember how I said if you take the same differential and you wedge it against itself, you get 0. So if we had dx wedge dx, we get 0. Well, this is going to come very in handy because we can, again, using this property and the fact that we can distribute our wedge product, we can say, okay, well, we know that we have a dy, wedge a dy. That's going to get rid of that. And we have a dz, wedge a dz, going to get rid of that. Because it doesn't matter, we throw another dy on there, because it's just going to die because we have the z or the y in this case going to bring that term to 0. Same thing happens here. We get rid of the x, get rid of the z. Same thing here. We get rid of the x, get rid of the y. So what are we left with? Well, we have del p, del x, dx, and then wedge dy, wedge dz, but we can then convert that back to out of wedge form just by removing the wedges. Okay, plus same, so del q, and what survived was del y, and then same thing dx, dy, dz. What survived here? Okay, del r, del z, and then dx, dy, dz. So we can factor this and say over here that this is going to give us, right, we have del p, del x, plus del q, del y, plus del r, del z, times dx, dy, dz. And this is amazing because this, del p del x plus del q del y plus del r del z, that is nothing more than the divergence of f. And if you're curious what the divergence means, I said it's really the dot product between the gradient vector, pseudo vector, and f. So what that looks like, if you're interested, is just going to be del x, del y, del z, and multiply not just p, q, r. And that's just going to give us del p plus del q plus del r. That's the definition of the dot product. Right, so this is the gradient dot f, which is the divergence of f. So that's what that is, the divergence of f, and then dx, dy, dz, that's just dv, right? Because we have, again, 3 dimensions. So we have our x, our y, and our z. So that's our we're taking the volume, obviously, we have 3 dimensions. So the divergence of f dv. And so we have just proven it. We've shown that since omega is nothing less than f dot ds, and that d omega is nothing less than the divergence of f dv. We have proven this, and we can thus happily conclude the double integral over s of f dot ds is equal to triple integral over e, the divergence of f dv. This is what we were trying to prove. We've just proven it. And again, conceptually, as we just said before, this makes sense because we're taking the integral over the boundary of our manifold of a function. And that is equal to the integral over the entire manifold, the entire region. But we're taking the integral of the derivative of the function. So there we go. We have proven this both conceptually and mathematically. We are done. That was a long video on the general Stokes theorem, but that's it. And you can really do this similarly with any of the other equations that I talked about earlier. It's going to be the same deal, defining your first writing your expression of the general Stokes theorem, then defining omega and f, figuring out then what omega is representing with respect to f, then same thing, take the derivative of omega, your partial derivatives and wedge products, and eventually simplify it something, you'll end up right with an expression that gets at the derivative of that function. And then you can celebrate because you are done. And this is really fun. And so if you haven't taken calculus, or you haven't taken vector calculus or multivariable calculus, take it. It is so fun, because I tell you, coming upon this was like finding a gold nugget finding not just a gold nugget, finding El Dorado after I've been wandering in the jungle, trudging through mud and fighting off snakes, right? You know, trying to memorize all those formulas, trying to think about that, because the general Stokes theorem, it really explains something that you can kind of think about conceptually, and that's the beauty. You can think about, you have the conceptual, but you have the mathematical approach to thinking about it, and it's really wonderful, and it's the beauty of calculus. It's just absolutely amazing, and it's awesome. That's only word to describe it. It's awesome. It's powerful. It's awesome. It's amazing. You know. So hopefully this was a very informative video for you on the general Stokes theorem, and hopefully you're interested to learn a little bit more about it. I'll put some information in the description, and hopefully you want to maybe try to prove more of these expressions. I know you have a lot of fun doing it. So have a great day, have a great year, great new year, right? As this is New Year's Eve. And make sure to add having more fun with math on your New Year's resolution. And I'm sure you'll enjoy it, and it really will change your life. You know, mastering mathematics enables you to master the language of the universe, and if you can do that, then you have really the ultimate power. And so have a math-tastic day, year, century, wait, decade, century, millennia. Have a math-tastic whatever. Thank you so much.